So, if you recall what we were doing in the last class, so in the last class we were looking at steady state error analysis, right. So, that is what we were looking at. So, let us say we consider the standard negative feedback system whose block diagram is represented like here, right. So, here G of s was essentially C of s times P of s, right. So, G of s is the forward path transfer function, H of s is the feedback path transfer function, and G of s, H of s is the open loop transfer function, right. So, we figured out that the closed loop transfer function was G of s divided by 1 plus G of s H of s, and the transfer function E of s divided by R of s is going to be equal to 1 divided by 1 plus G of s H of s, right. So, those are the two critical transfer functions that we are going to be interested in, and using this we got that E of s is R of s divided by 1 plus G of s H of s, right. So, that is something which we are going to look at in detail today, and using the final value theorem, the steady state error, which is essentially nothing but limit t tending to infinity E of t is limit s tending to 0 s times E of s, which is given by limit s tending to 0 s times R of s divided by 1 plus G of s H of s, right. And we discussed that if G of s H of s were to take this generic form as shown here, we can always rewrite it in this form, right. Some k times some numerator polynomial whose constant term is 1 divided by s power capital N times a denominator polynomial whose once again constant term is 1, right. So, that is something which we discussed in the previous class, and depending on the values of n, okay. So, we call the corresponding system as a type n system, okay. In general, it is what is called as a type n system. So, if n is 0, it is called type 0, if n is equal to 1, it is called type 1, and so on, right. So, and today we will see what is the what to say at least concept that we associate with this value of capital N, right. So, that is where we stopped in the last class, okay. So, today let us continue from where we left off. So, we are looking at the steady state error. So, let us first do the steady state error analysis to a unit step reference input, okay. So, that is what we are going to do to begin with. So, let us take R of t to be 1 and let us observe what happens, right. So, that is the first analysis we are going to do as far as steady state error analysis is concerned. So, if R of t is 1, what is R of s? It is going to be 1 divided by s, right. So, this immediately implies that the steady state error, which is limit s tending to 0 s times capital R of s divided by 1 plus G of s H of s, that is going to be equal to limit s tending to 0 1 divided by 1 plus G of s H of s, right. This can be rewritten as 1 divided by 1 plus G0 H0, okay. So, essentially where G0 H0 is nothing but the value of the open loop transfer function evaluated at s equals 0, right. So, that is what it is, right. So, using this we define what is called as a static position error constant, okay, which is denoted by KPE, that is defined as limit s tending to 0 G of s H of s, okay. So, that is a definition, okay, that is a parameter. As we progress, we will see why it is called as a static position error constant, okay. So, right now we will just define it. So, the static position error constant is nothing but the limit s tending to 0 G of s H of s. So, this would immediately imply that the steady state error is going to be nothing but 1 divided by 1 plus KP, right. So that is what we will get, okay, for the steady state error to a unit step reference input. So now let us look at what happens when n equals 0, when n equals 1, when n equals 2 and so on, right. So what do you think happens to KPE when n is equal to 0? When capital N is equal to 0, so that means that in the open loop transfer function, I am not going to have an just factor of s or any higher orders of just s in the denominator, right. So if I take the limit as s tending to 0 of g of s h of s, what will happen? I will get only k, right. So because s power n is not there, right, because capital N is 0, am I correct? So when capital N is 0, so I will just get k times b naught hat s power m all the way till 1 divided by a naught hat s power p all the way till 1, okay. So of course p becomes equal to small n then, right. So then you immediately see that if I take the limit s tending to 0, what happens? I get k, okay, which is what is called as open loop gain, okay. We will see, we will encounter it later, okay. So that is what we are going to get, and as a result, what is going to happen to the steady state error? We are going to get it as 1 divided by 1 plus k, okay. Is it clear how we got it as 1 divided by 1 plus k? Because KPE becomes equal to capital K. Now if n is equal to 1, what do you think happens to the value of KPE? If n is equal to 1, what do you think happens to the value of KPE as s tends to 0? So immediately you see that the limit of s tending to 0, g of s h of s will become infinity, right. So what will happen to the steady state error? It will asymptotically tend to 0, right, and that is going to be the same case if n is equal to 2 and higher, right. So that is what we will get, okay, for different values of n, okay, when we want to track a follow a step input. Yes.
Is there a condition for m and n with numerator denominator power?
Anyway, we are considering causal systems, right. So m is less than or equal to small n, okay. Capital N plus p is equal to small n, okay. So that is, those are the constraints that we are. So please note, like, see, of course from here onwards I am not going to tell all the adjectives before the word system, right. So that we looked in the first few classes, right. Throughout this course we are going to be interested in single input, single output, linear time invariant, causal, dynamic systems, okay. That is frozen, right, unless otherwise I say so, right. So, so obviously like we are going to work with proper transfer functions. So that means that m is, small m is less than or equal to small n, okay. Yeah. So yeah, so this is the steady state error for a unit step input. So what can we observe from this? What can we conclude? So we can immediately see that, of course, when we write this, please note that capital K is what is called as an open loop gain, okay. We will see why it is called that way, like, okay. So it is called as open loop gain, okay. So so then when so what can we observe, right, so from this analysis? So what we have done, we have given a of course please note that we are assuming that the closed loop system is stable, right. So then only we can do all this analysis, right. So that's a presumption, right. So when we provide a unit step reference input, right, so when do you think we would be able to track the or follow the unit step reference input perfectly as time increases? We need at least a type 1 system, right, because if it were a type 0 system, I can follow the unit step reference input, but with a steady state error of 1 divided by 1 plus capital K. Of course, one can say that, look, let me increase capital K, by some means. But you will see that if you cannot increase capital K, because capital K will be tied with the control effort that you need to put in. So we cannot just increase the open loop gain to whatever value we want. Okay, in fact, like when you come to automotive controls and other courses, you will be able to physically realize what capital K is, right? So you will see that will have something to do with the actuator specification. See, for example, if you want to steer a vehicle, what is the capacity of the steering system, right? For example, right? If you want to brake a vehicle, what is the capacity of the brake system, for example, right? So you have a limit on that, right? So I cannot keep on increasing capital K. Mathematically I can do it, but physically I may not be able to do that, right? So one can see that if I give a unit step reference input, okay, if I have a type 0 system, okay, so let's say this is my reference input R of t. So let's say I give this is my R of t, right? What will happen is that my y of t, if I have a type 1 system, may essentially settle down like this, okay, with a steady state error. Let's say, sorry, if it's a type 0 system, okay. So you see that the steady state error is going to be 1 divided by 1 plus capital K. Okay, so there is going to be some finite error, right, as time tends to infinity. So, but on the other hand, if I have a type 1 system or higher, I can at least theoretically guarantee that the steady state error is going to go to 0 as time increases. Okay, so then that means that like this is indicative of, in this case, what we call as tracking error. That means that like I give a step input to track. Okay, that is what I want to follow. So the word tracking means following some desired signal or desired profile, right? So I want to follow a unit step input, unit step reference input, I give it. See, for example, see, let's say, like if you want to essentially steer a vehicle, right? So for example, let's say you want to give a unit step change in the orientation of the vehicle for some reason, right? So then the question is that, can your vehicle essentially achieve that as t tends to infinity? Okay, so that's what we are looking at, right? So if my plant does not have a pole at the origin, that means it doesn't have a 1 by s term. How can I introduce a 1 by s term in the open loop transfer function? See, typically P of s is given to us, it's what the system is. Let's say the P of s plant transfer function does not have a, so as an example, let us say P of s is, let's say, something like 1 by s squared plus 1, there is no pole at the origin. Then let's say h of s is 1. Then how do I introduce what to say, let's say, let me put it this way, s squared plus s plus 1, okay, for example, right? So then how do I introduce a pole, there is a pole at the origin or a 1 by s term to make it type 1? I need to use an integrator, right, in the controller block. Okay, so that's what we discussed, right? So I told you that integral control can guarantee you 0 steady state errors if you want to essentially follow step inputs, right? So now you can observe why, right? Suppose, so that's why we need to take it with a pinch of salt. Okay, we need to look at these things very carefully. If my plant transfer function already had, if P of s were like 1 by s plus 1, I don't need an integral controller to make the steady state error go to 0. I can use, let's say, proportional control itself. Okay, so the main key thing is that if I want to track a unit step input with 0 steady state error, the only thing I need to check is that, like, does the open loop transfer function have a 1 by s term? Okay, that can come from the plant, it can come from the controller. Okay, so if the plant already has a 1 by s term, I don't need to use integral control, but if it does not, I need to use integral control. Okay, so now you understand the reason as to why people say that integral control can drive the steady state error to 0. So if your plant does not have an 1 by s term, if you just use proportional control, you are going to get a steady state error like a type 0 system, right? That is what we discussed when we discuss various controllers, right? So, I am sure slowly all those points are getting clarified, right, as we go further and further in the course. Okay. So, I hope this point is now clear, right? Okay. So, that is the what to say. So, if P of s is 1 by s times s plus 1, okay. So, we do not require I, okay, a integral term in C of s for driving the steady state error to 0, okay. So, that is what completes that sentence. Is it clear? Okay. So, but then we will shortly see, you know, like when we go to the root locus and other analysis, that see purposefully introducing a pole at the origin, you know, like has a counteracting effect, okay, nothing comes free, okay. So, if we introduce a 1 by s term through our integral term, okay, for this purpose, what I am going to have is that I am going to have an open loop pole at the origin, then stabilizing the closed loop system and getting closed loop performance are going to be relatively more challenging. So, there is a price to pay, all right. So, the control design needs to be done more carefully, fine, okay. So, that is to a unit step reference input, okay. So, the second input which I am going to consider is steady state error to a unit ramp reference input. I am sorry, what is it? Not in that sense, you know, like, but the thing is that, like, the question boils down to, you know, like, what are the typical inputs you need to follow, right? You need to track. That is a question we need to ask ourselves, right? Based on that, sometimes we can intuitively adjust the open loop transfer functions and design. Okay. So, the design goes both ways, you know, like, see, for example, in one of the recent work we did, you know, we looked at the data and then hypothesized the transfer function, you know, like, because based on this analysis we know what structure will satisfy or fit the data, right. So, it is a two-way process, right. So, just not that, you know, we always go one way, you know, like, and do a universal control design, no. So, it really depends on what we want to track, okay. So, so suppose if we want to, please note that unit ramp is not a bounded input, right, that is point number 1, okay. Kindly remember, see, if ever, you know, like, we figure out the value of a function of y of t for a unit ramp and we observe that the output is going to infinity, naturally it would, right, because it is not a bounded input, okay. So, please remember that, right. So, R of t is t, right. So, that means that R of s is going to be 1 divided by s square. So, this immediately implies that I am just repeating the same calculations, limit s tending 0, s times R of s divided by 1 plus g of s h of s, sorry, what is going to happen. So, what will happen here? I will get limit s tending to 0, s times 1 by s squared, right. So, 1 s will get cancelled, I will be left with one more s term. So, this will give me limit s tending to 0, 1 divided by s times g of s h of s, okay. So, then the term static velocity error constant KVE is defined as limit s tending to 0, s times g of s h of s, okay. So, that is the static velocity error constant, that is once again a definition. So, immediately we see that the steady state error for a unit ramp input is going to be just 1 divided by KVE, okay. That is what we have, right, okay. So then we do a similar analysis now for n equals 0, n equals 1, n equals 2 and higher, right. So what do you think would happen now when n equals 0, 1 and 2, what happens to KVE? So KVE is going to be S times G of S H of S, right. When for a type 0 system, please note that there is no S term in the denominator, right. What would happen to this limit? It will be 0, right. Please remember, what is the structure of G of S H of S? This. So for a type 0 system, S power n capital N term does not exist, right. You multiply by S, take the limit S tending to 0, you are going to get a limit S tending to 0, S times K, that is going to be 0, right. So that is why we got KVE as 0 for a type 0 system. So the steady state error is going to tend to infinity, right. So it is going to become very, very large as we go on. Yes.
So why are we setting steady state error for an unbounded input?
Unbounded input. Okay. So sometimes you may want to track it. Okay. So sometimes you may want to track a ramp. Okay. The question is that what structure I need. Okay. So that's the objective of this analysis, right. So we will see that, like it's not a very simple straightforward problem, right. It really depends on what you want to do in practice. In some applications, let's say you want to track a signal, like which goes like a ramp and maybe then reach a steady state. What structure would you want to essentially track it very closely, right. So you can see that with a type 0 system, we are not going to we are going to have a significant steady state error, right. So and as t, if you maintain the ramp forever, your steady state error is going to go to infinity. That's what we can observe. Is it clear? Now with a type 1 system, what will happen to KVE? Type 1 system means there is a S term in the denominator. So you multiply by S, the S and S will get cancelled, right. So as you take the limit S tending to 0, what will happen to this KVE? It will become capital K, the open loop gain, right. So what will happen to the steady state error? It will become 1 by K, right. Correct. So type 2 KVE will be infinity, type 2 and higher, and consequently the steady state error will be 0. Okay. So what this means is that, like, if I want to track a signal which goes like a ramp, if I use a type 0 system, then I am going to get very high errors, right, tracking errors. Okay. Of course, if the ramp is only for a finite duration, then we may still live with that error, right. But if I have a type 1 system, at least I can get reasonable tracking, okay, with a steady state error as 1 by K, capital K. Okay. Of course, higher the value of open loop gain, lower will be the steady state error, but once again the same constraint comes in, right. If you increase capital K, there is a cost as far as the control effort is concerned. Okay. And if you have type 2 and more, theoretically you are guaranteed that the steady state error will tend to 0. Okay. So that's the thing, right. So but obviously if you want to track a ramp with 0 steady state error, you need a 1 by S squared term in the open loop transfer function, right. So that's like a double integrator, right, and you introduce 2 open loop poles in the origin, right. So then we will see that it becomes progressively more and more difficult to in fact stabilize the closed loop system. Okay. So we'll look at those constraints, right. So but this is what you have. But another reason why I am doing this analysis is also to introduce you to these terms: static velocity error constant, static position error constant, and what is called a static acceleration error constant, okay, which we are going to come to now, right.